And this brings us finally to motion detection. To do motion detection, essentially, we detect outliers in images. The outliers will be the motion. So what we will do is that we have images taken periodically by a web camera. If it was a movie, maybe you would get 10 a second, but in this case, we will have one image per second in our example. So you have many images, one per second. Normally, nothing changes. So normally, the next image is very close to the average of the previous ones, right? Closer than the standard deviation. But if there is a car that passes or a person that walks by, then suddenly that's a much bigger difference. And we should be able to detect it as an outlier using really the previous techniques. So how are images represented? Images are represented as matrices. They have size, in our case, of 640 by 480 by 3, where the 3 are for the 3 color channels, red, green, and blue. Okay, so I prepared some code for you already. There are some images that are on a server that I put up on the Google Cloud. And so here is some code that actually reads the images and fetches them. Let me just comment very briefly. Pill is a Python package that helps you deal with images, and especially image encodings in JPEG, PNG, and so on and so forth. Requests is a Python package that enables you to very easily access HTTP resources. So fetch essentially data using the HTTP protocol. You can fetch web pages, and in this case, you can also fetch data that is consisting of our compressed images. Zip file is used to deal with zip files, as the name says, and I/O is a module that that is a Sardinian equivalent for hurry up. No, let's go in Sardinian. No, I/O is actually a module that stays for input output and is used to essentially build files out of strings. Let's see how it is all put together. This is the URL where the data is. I request that the data at that URL, it's put into R, the result, R.content is the data that I fetched. The problem is that zip files is not able to unzip a string. It's only able to unzip a file. And so this bytes.io is essentially building a file out of the string that is the result of the request. Once I have the file, I can use the zip file module to decode it. Okay, and for every file that has been zipped into your larger zip file, this represents an individual image. I open it, I read it as an image, and I put the image converted into NumPy in an array of images. So this code, probably took me, I don't know how long, but certainly more than a few minutes to write, because I had to search for all these resources and figure out how everything works. But this code is quite compact, and I invite you to study. It does a lot of interesting stuff in a very short format. And at the end of it, we have this array of images, each one of which is represented in NumPy. So let's run it. This will actually go out and fetch the images. So you need to have internet to run these, obviously. And then I can print the shape. What's the shape of the zeroth image? Oh, 480 by 640 by 3. This is because a matrix is stored rows by columns by the color depth, and the rows is like the height. So it has height 480, width 640, and 3 colors each. I can print the value at a particular pixel. This image 0 at pixel 1022, and it happens to be 225. So pure maximum color. In an image, the values at each pixel go between 0 and 255. So now we have the sequence of images, and the crazy thing, a marvelous thing, depending on your point of view, is that we can actually feed these images to our discounted averagerator. This seems crazy because we have written our averagerator as if it was to deal only with numbers. And now we are instead of numbers, we are sending it whole matrices at a time. But the fact is, this works. because NumPy, if you ask to sum 0 plus a matrix, it will duplicate or replicate the zeros for all the elements of the matrix, and it will be able to do the sum. So NumPy, Python has this virtue that by not checking types, it sometimes lets you generalize code that you have written for one application to a much more general one. And in this case, well, I paid attention when I wrote the original code, but in this case, we can really use the discounted average to work on images. And we can give it a spin. So this is our discounted average class again. I cut and pasted it here so that you can read it again and convince yourself that it works also for matrices. The reason is, let's pick a place and read it, okay? Imagine X is a matrix, and this is the first image that you, first matrix that you give to the discounted average. What will happen? Okay, the weight update does not involve any matrix. The sum of the x's, it will say self alpha times self dot sum of the x's. Sum of the x's initially is going to be 0. So this is just a floating point, right? This product from here to here. So you have a floating point, which is actually going to be 0 plus x. And NumPy is kind enough that when you add a number to a matrix, this is the image matrix, it's able to do it. It will just add the number to all the elements of the matrix. So this for the first time. For the subsequent times, this sum of the x's will be a matrix as well. And then, alpha times the matrix is easily done. It will simply multiply every element of the matrix by alpha, and then it will add x. So miraculously, everything works. And we can see that it works by actually spinning the wheels. So here I essentially feed to the discounted average just the first 10 images. Okay, I do that. And so here is the result. Here is the first image. You see, sharp, quite well, not super sharp. The webcam was so quality. But reasonable quality sharp. This is the average of the first 10 images. You see, there was a bit of wind, so the tree was moving, and the average of the first 10 images has a sort of blurry tree branches here in the foreground, because they were moving so much. And if you ask for the standard deviation, you can also plot it. We need to plot it independently for the 3 channels, or we could decide to, show the sum. In this case, I show it for each color channel separately. And the one for the red channel looks like this. Green channel and blue channel. So you see, the standard deviation has high values where the 3 branches are moving and is fairly low elsewhere. So if there is something that moves in the image here, like a car that enters the image, we should see that the difference between the new image and the average is much bigger than the standard deviation, which here is pretty low really. Okay, that's our idea for detecting motion. And so I actually leave it to you to write the motion detection class, because it's kind of fun. And I just want to be able to use it. So I write this detect motion function. I do as follows. I create a motion detector instance, okay, from your class. Then I read the images, okay, and each time I read an image, I feed it to your motion detector, which has a method detect motion to which I can pass an image. And as answer, I will get how much motion there is in that image, how many pixels have moved. In how many pixels did you detect motion, okay? And if you detect motion in at least 500 pixels, just to check that there is a big enough motion, I will say that motion has been detected and I remember in which image, okay? So I can define this class, then I can run it on my sequence of images. It may take a little while, and then I can visualize all the images in which there is motion, you see, because I kept track of them in this list of detected motion. So now I can, which I passed to motions. So now I can go over it and display the motion that I detected, okay? And so here is what happens. Let me go back to the beginning here. Okay, so there is motion initially. Well, because initially you don't know really well what the average and standard deviation are, and so you have a few spurious motion detections at the very beginning. This is quite normal. So the image 1, the image 10, in reality there's nothing that moves, so these are just spurious. But then you start having good results. You see, from 10 to 47, there is like 37 seconds, you don't detect any motion. Now you start detecting motion again. What is happening? You don't see it very well by eye, but if you look at the pixels that moved, something there. You see the nose of this car, there is a car nose intruding into the picture at time 47. And the next motion detection is going to be at time 48, in which this car that nosed into the picture there actually is here, smack in the center. Okay, and so the detected motion is right here. And then 49, the car is now here, and the detected motion is there. Okay, correspondingly. So this idea to detect motion really works, and you can look at the instruction from implementing your class. Now, let me give you some hints on how you can implement the motion detector class using NumPy. The idea is as follows, roughly. You have one image, and the image is 480 by 640 by 3, right? You have 3 color channels. So you have images that are sort of these parallelepipeds or blocks that go around, right? You have one image, you have another image, you have many of these blocks. And at some point you have the most recent image, let me call it IMG, actually let me call it just X, okay? You have this image X, and you also have the average, which is again a block of the same shape, right? Because the average averages independently every pixel of every color channel. So this is X and this is mu, your average. And I just want to point out that in NumPy you can very well compute the difference between X and mu. So this is the difference between your image and the average values for each pixel. Once you do this, you can very well compute whether this difference is greater than a certain threshold, okay, theta, which can be constant or can depend on the pixel if you want, right? This you have to reason about. But if you do this operation, if you do this comparison, what you end up with is again a block that instead of being full of pixel values is full of Boolean values, because it's the result of comparing each color of each pixel with a certain threshold, right? So so here the elements of this object will be true or false. We have already seen in the introduction to NumPy that I gave you that individual values in matrices can be also Boolean in type, and that if you do a comparison between a matrix such as x minus mu and another matrix such as theta, what you end up is a Boolean matrix, right? So now the problem you face is actually not very complicated. This Boolean matrix here has, again, size, like everything else, 640 by 480 by 3, because everything has that size. But the motion you want to detect is only 640 by 480. So the idea that I tell you to use is this. Declare that there is motion in a certain pixel if there is motion in any of the color bands associated for that pixel. So you have essentially this matrix, which is 480 by 640 by 3. You have to compute the maximum along this dimension for each pixel. And this I told you how to do it, because essentially what you need to do is you need to say max of the matrix, let me call it A, of the matrix A, with an axis that is equal to, remember the axis is what you have to eliminate. So if your matrix has a shape 480 by 640 by 3, the axis is, this is axis 0, this is axis 1, this is axis 2, so the axis is gonna be equal to 2. And so this will enable you to collapse this matrix of booleans into a matrix of booleans that is simply 640 by 480. So this is a general idea of how to do the motion detection, okay? You can feed your images to the averagerator. Out of it, you can get easily the average and the standard deviation. You can compute the difference between your image and the average. You can do Boolean comparisons. This gives you motion detections for each color of each pixel, and you can compute the essentially logical OR along the 3 color bands for each pixel by using this maximum on the second axis, okay? So this should give you enough hints of how to put together all the various operations in NumPy in order to achieve this outlier detection that gives you the motion detection.